Welcome to the last session of our meeting, the third day of our meeting. And the first speaker today is Professor Susumu Tanabé from Galatasaray University. He is actually from Japan, but he is working at Galatasaray University and producing many nice mathematicians, young mathematicians. He is also expert in many different languages. So let's hear Susumu.
Yeah, thank you very much for the presentation. In fact, I shall apologize for the subject of my talk that concerns rather algebraic geometry and special functions, and not really the number theory. So, but my apologize goes to the fact that special functions, especially the hypergeometric functions, so this many variables case, played important role in number theory. So you recall the Picard-Fuchs equation, Gauss-Mann systems, and so on. So I think that it can be interesting. So in case it does make a part of the great science that we are engaged. And also that I hope that the next meeting that shall take place in Tehran at IPM, a certain moment, I will try to prepare a talk on Dwork cohomology, Dwork zeta function, Dwork crystals, and so on. And the motivation I explained right now just before that my interest in to really understand the Persian poetry of Methnavi and Ghazali and Hafiz. That also additional somehow quite strong motivation. And I certainly want to go to Tehran and IPM. And maybe if I have a chance to discuss with you on the possibility to collaboration between Pedagogy Institute in general, and Turkey and Iran, I have some proposal. I worked on that. Some 7 years ago, there was a project, such kind of cooperation, development cooperation with French, but if there will be time after the meeting, I can share my experience with that. So let me begin. I shall mention that why I'm here, because it is courtesy by friendly proposal by Professor Yuhan Ikeda, is my neighbor. So we're university quite near, and we have two common master students, and they follow his seminars and my seminars, and so that we are somehow very in tight cooperative regime. You see, that's one of the reasons why I'm here. So okay, so let me illustrate somehow the content of my talk. First of all, I explain what the homological mirror symmetry, couple of concept is. And secondly, I explain what is the monodromy calculus by means of Mellin-Barnes integral for Gauss hypergeometric function, the very simplest case. And then later I go to introduce the toric geometrical setting with the aid of Newton polyhedron, defining and affine Calabi-Yau hypersurface. And then later I explain the cohomology of this hypersurface by means of so-called Stanley-Reisner ring that will give, that corresponds to really, that creates a connection between the basis of hypergeometric functions and cohomology. Yeah? And the third way is really the difficult part, the analytic contribution of hypergeometric functions. And I will show some examples. So, first of all, what the homological mirror symmetry is, that is so conjectural equivalence between two derived categories for Calabi-Yau variety X and another counterpart Y completely different Calabi-Yau variety. And between these two, dual Calabi-Yau varieties in duality relation, such kind of equivalence relation hold. That is, the left-hand side, you see that so-called Fukaya category of Y, variety Y, and on the right-hand side, coherent chief, there are category chiefs. So left-hand side somehow comes from a symplectic geometry, and right-hand side comes from a complex geometry. And somehow these two geometries are equivalent in a wonderful, miraculous way. And today, that if these are today, I will concentrate rather on the consequence. So this is conjecture; it is not proved. It is proved only very restricted cases of curves and so on. Elliptic curves, this kind of thing. Yeah. So. And today I will talk about this rather concepts, and that will shall support, supporting evidence to prove this homological mirror symmetry in the final form. That is, to compare not really the derivative category themselves, but rather auto-equivalence, isomorphism, even self-equivalence groups. So my talk will concern this so equivalence of the Fukaya category part, rather, my work concerns. And so our aim today's talk is to realize the essential part of this self-equivalence that is, in fact, the most important part can be expressed as the automorphism on homology group of Y, Calabi-Yau variety Y, and my method is to study this automorphism on monodromy. That is as by means of monodromy period integral. So monodromy, of course, and this is the coarse moduli space as a very high dimension, say capital N, and we should consider loops avoiding this differential loci. And so, and one of these loop, avoiding this loop, shall produce this kind of monodromy behavior. So this today's the aim of today's talk, my talk, is rather to explain this last expression. So even though it is written in one, it is so lambda is from study rational ring, so it is from vector function. You can associate vector function. Yeah. So it is really a monodromy, and you can write it down in a form of a matrix. And this matrix is completely governed by Todd class of X. You know that we are talking about the monodromy of Y, but the monodromy action is described by means of Todd class of X. So mirror symmetric counterpart variety. That is, that's the very, how to say, the one proposal made by Kontsevich, and there are many trials. This is, my talk is one of these trials to realize this view. Okay, so first of all, I want to recall what Gauss monodromy is, what kind of monodromy we will talk about. In making use of Gauss hypergeometric function, classical case, that is series that convergent in S, some small disk, unit disk, open unit disk S, and this allows us integral representation. So this means that if this Gauss hypergeometric function is nothing but, it can be considered for alpha, beta, gamma sum. It can be considered as a period of a curve of this type, x, y to the power n, something like that. Okay, S is it is a curve. So you know that this hypergeometric functions series satisfy differential equation, or second order differential equation, that's written below. But the important point is in this approach to the monodromy is to make use of Marin-Barnes integral representation, that is making use of gamma functions. So to understand this series, in terms of so series defined by a residue of a certain kind of gamma function. Okay, so and this say of course gamma function has poles to negative integers. So alpha plus z or beta plus z or minus z is negative integer. Then we have poles, and we can gather, collect these poles, like these poles, and to as you say that these are poles that extends to the negative direction, and this one is positive. That is correspond to the poles of minus z, gamma minus z. So it independent of this type of poles, the convergence domain changes. So Marin-Barnes integration. So this has Gauss hypergeometric functions equation has dimension 2 solution in linear independent solutions, and you know that there are two solution near s equals 0 or s in unit disk. There are two series expansions, there are series solutions of this f alpha beta gamma and s to the power minus gamma plus 1, etc. These two types. So these are obtained by means of this completely by means of this Marin-Barnes integral of representation, but you should change somehow periodic function to get these two different solutions. And now I explained how to get a global, and it's a gluing process of. So these the series that I presented was defined only in a small s near 0. But we want to get a global representation, that is, say, to look at the solution, what analytic continuation of these solutions to s equals infinity, and this can be achieved by means of so-called Marin-Barnes integral contour throw. So remember that there were two types of contours. Yeah? And but Marin-Barnes integral is universally valid. That is, say, S can be can be everywhere. So far as it converges. So we are allowed to do this kind of contour throw to get analytic continuation of at s equals infinity from solution Gauss hypergeometric function s equals 0. And the result is the following. So this is a normalization kind of. So you see that s equals 0 part functions solutions can be expressed by means of S infinity solutions by means of so-called connection matrix. So the point is, in fact, for these, if you fix one solution basis at S equals infinity, then each of the behavior of each of them, monodromy behavior, each of these, Y1 bar star and Y2 bar star is quite easy to understand. But what is the behavior of Y1 star and Y2 star at S equals infinity? What happens then? So that's our problem. So, and that can be achieved by means of this connection matrix, you know. So if you know connection matrix, we get the information, we can restore completely the global monodromy by making ingluing local monodromy and infinity, S equals infinity monodromy, because Gauss hypergeometric function has only three branching points, decreasing the points. So the this fundamental group, phi1 - 0, 1, infinity, is generated by two loops, 0 and infinity. So the loop around 1 can be restored from loop from 0 and infinity, and monodromy can be reached in this way. So if you know these two monodromy, then we get H1 also, and we get everything, okay, global monodromy. So this is how to say, kind of model to be done. For the case of affine Calabi hypersurface generalization, I will talk about the. So the geometrical object, the main geometrical object for which I calculate period, is given by this equation. I consider affine and torus, algebraic torus. I consider this, and A, this capital A, correspond to this deformation parameter, where the discurrent lives. And I will follow the deformation of homology and cohomology and period of this variety, depending on parameter A in a global manner. Okay. And but I impose the condition that these Newton polyhedron of this not f cell rather itself, but xn times fx plus 1, that is a kind of convex whose Newton polyhedron will be a convex hull of Newton polyhedron f and 0, such kind of Newton polyhedron will play an essential role further. And associated to this Newton polyhedron, a matrix, n times large n. Large n is always the number of terms, okay? Small l n is number of the dimension where this of algebraic torus of ambient space, small n ambient space. And somehow impose this Gorenstein-Kohn condition that these, but as you see that there are too many parameters of deformation parameters. There are too many different parameters, but we can consider quotient, torus action quotient, to get some Chow group of rank small d equals large n, the number of terms of the defining equation minus dimension of the ambient space. So in fact, not only n, but all these numbers play important roles as essential data in further. So small d will be the rank of Chow group of the toric variety, defined by this fan. And now the essential gradient, the following essential gradient will be the following. that the relation as D, the relation, so this D is small d, assumed to be strictly positive, greater than 1. There lies relations between these vertices of the Newton polyhedron, and they form a kind of lattice that I denote by L. And the generator, I choose some kind of generator that is a L1 or a vector LD. And this, so I get a matrix of D times, so we have D matrix, D times N, D times N, large N matrix. That is called the gate transform of the matrix A. And this gate transform will define, will contribute to the description of the period integrals of GKZ Hypergeometric functions. And there are some conventions there. We need to some classification of indices in 3 types. This is somehow cumbersome, but so this I write here. I write yes. So this is somehow procedure with which kind of on which kind of coarse moduli space I will work further. Instead of A itself, A is so in torus, algebraic torus of dimension large, and I consider S variable S S1 to S, so number with D, only D variables. So in certain cases, it really becomes 1 variable function, Hypergeometric function, Pohama Hypergeometric function that can be treated in a classical manner. So that's fine, nice. And this is the case when a K3 surface appears. Let us look at P2 times P1, K3 by degree 3 K3 surface can be defined by such a Laurent polynomial. So affine part is defined by this Laurent polynomial, and vectors, so vertices that take part is so A1, this vector is 1, and this one is here, and this is here. So this is x4, exponent x4 is always 1. So we have 4 times 6 matrix, and what do I get? What is the gate transform? This is the relation between these 6 column vectors that is given by this, and so I get the gate transform as these 2, and as a result, this torus action quotient of moduli variables and deformation parameters. We have this form that is completely given by these parameters. Yeah, okay, this part. 1, 1, 1, 1, 1, 1, minus 3, and so on. So the main object, what is the how do I study this residue? No period. Rather in the form, it doesn't matter. It is a kind of you can consider it as simply the coupling of homology and cohomology. But somehow, some technical reason, I prefer to do it by means of so coboundary. I can kind of residue along the hypersurface defined by this. So it's just so nothing but Cauchy's integral formula and several higher dimensional case. So this, if you consider this so this is function in A, you see. This ramifies somewhere, of course. And to study it as analytic function, kinetic continuation, we look at differential equation, that is global object. You see, series, local object, differential equation, global object. So we can do it. It's reasonable to work with differential equation. Okay, so it satisfies this system of GKZ Gelfand-Kaplan-Zerbinsky Hypergeometric function, Gelfand-Kaplan-Zerbinsky Hypergeometric functions. First is somehow looks like the wave equation. Second is weighted homogeneous to degree 0 in A, and the third one is homogeneous degree -1 with respect to the final variable xn that was multiplied everywhere, and this dimension of this system equals to volume of the Newton polyhedron itself. Very nice. So combinatorial description is given. So this, of course, is the basis of everything to calculate monodromy. So if I to relate this, so this was a differential equation, system of differential equations, but I want to represent it to study it by means of Manning-Barnes integral. To do this, it is convenient to do this quotient, torus action quotient procedure to get smaller number of variables. Instead of A parameters, I consider S parameters. S is dimension D, okay, n minus n. And in this situation, and I can represent this period integrals power series. Of course, we should discuss that convergent domain somewhere, yeah, as a residue, summation residues of this kind of gamma function expression. And the important thing is that B1, BP, these are all from gauge transform. You remember this. So gauge transform like this. Like this. So gamma function, transcendental, and if and you take, I take some residues in a scrupulous manner to get convergent series somewhere in d-dimensional space. And convergence domain story has has a very nice description thanks to the theory of Gelfand-Kaplan-Zerbinsky theory on A discriminant. Secondary is fan and so on, secondary fan construction. So I simply show you this kind of dictionary exists between the convergence domain and regular triangulation of delta F, that is a Newton polyhedron, and the vertex of the secondary polytope of A. Secondary polytope, roughly speaking, this is the Newton polyhedron of the discriminant also. I will show you later. So in the case of this example, and in the K3 surface case, secondary polytope looks like this, only 3 vertices. And you see this associate, there's 3 combs can be associated to each. And if I gather all of them, this will really give a fun, really closed. This is very important, remarkable fact. In further discussion. So, the counterpart to this GKZ hypergeometric function, GKZ differential equation series system in the SJ small d dimensional space will be so-called Horn type or hypergeometric system. So again, here BPs, these are all come from Gale transform. So this is a Pohama symbol, and this is, yes. So I have this kind of system of equations, D tuple, small d tuple is J. J runs from 1 to D. So I have D tuple of so-called holonomic, you know. This is D module story is also related, of course. So Beilinson, Berenstein, the pervert sheaves, of course. So this is phi gamma. Concretely in this situation, in this case of K3 surface case, I can consider this kind of residue, so bearing bonds in interval, and the sum. For example, P1. Where is P1? Oh, P1 must be here. Somehow P1 must be the residues of poles produced by these factors. Z1 equals positive, Z2. Here I write it. Yeah. Okay, this is one of the, and the dimension of this hypergeometric system, Horn hypergeometric system is 6. Now I pass to the description of cohomology ring by means of so-called Stanley-Reisner ring. And this is achieved by means of this polyhedron vertices of the Newton polyhedron that appeared at the very beginning, defining function. And also, yes, everything can be given by this. There are two types of ideals to be considered: linear part and some monomial part. And that is known since Danilov, Vladimir Danilov's or Fulton. I don't know. It is well known fact. So and and the ideal somehow B, the gate transform appears also here. Gate transform B appears also here, and the Stanley-Reisner ring description also. But nothing. I use all the time these gate transform EP. And this was, so our A was so this Stanley-Reisner ring, initial one, this was somehow affine cohomology, variety. And if you want to get compactify and a toric compact toric variety in the cohomology of the hypersurface compactification, then you need to take a quotient more. Somehow this kind of, this. Annihilation of core is very interesting polynomial, shall be. Ideal shall be considered, yeah. And now further, I restrict myself to the Gorenstein case to consider Calabi-Yau, and it is so it generates and so integer lattice, and that there exists one that is somehow located on a hyperplane. That is our case, of course. And the Gorenstein is called reflexive. That is new condition, completely new condition that if dual cone is also Gorenstein, that is Batyreff's somehow mirror construction. This appeared, and this is the so synchronous. So how it is related to our GKZ hypergeometric function? Why it is reasonable to look at monodromy of GKZ hypergeometric function to study the monodromy of homology of the variety. Calabi variety is relies on the following fact that there is an isomorphism between this standardized ring and the GKZ space of GKZ hypergeometric functions. Yes, toric geometry and hypersurface, period integral. So, if I pass to the toric quotient in dimension small d space, then it will be Picard equation. Yeah, that's a bit subtle equation that maybe I have no time. So I show you how it looks like this standardized ring. And a affine variety has affine K3, affine part of K3 surface as rank 6, as we have seen, and we have very concrete, very simple, how to say, rectangle description, but to pass to really K3 surface, and P2 times P1, yes, compact K3 surface, we need to take a quotient by some another ideal, and we get dimension 4 space. That is toric variety, and so compact space. That can be extracted, subtracted from the first the space. Everything can be done starting from this Newton polyhedron construction. So now I pass to the topology of the moduli space. That is topology of the complement to the different discriminant loci. Okay, I rather work on small dimensional space. D small d dimensional space, and amoeba is so-called amoeba is the tropical geometry basis. There is a log image of discriminant loci that is well defined only on this intersection with torus, and so this one. So log D in outside of log D, and we consider as a inverse by log image. Here will be the convergence domain. That is, and so the domain where the variety, affine variety, is irregular. That is, say, period integral is analytic. All of period integrals are hypergeometric functions, are analytic functions in a neighborhood every point. Okay, and there exists very nice description in terms of this amoeba, in terms of the secondary polytope, in connection with convergence domain of period integrals. So I recall this dictionary between that exists in secondary polytope construction, secondary fan. And finally, we get secondary fan, thanks to Gail van Kaplan-Zarabinsky. So I illustrated. So in the case of K3 surface, we have amoeba like this, and we have three disjoint union of components, complement components to amoeba. This is amoeba, log image of discriminant, okay? And these are the domain, log of convergence domain. We have three. So there are three recession cones, so-called cones. We have three cones. It is, and there are three types of convergence series to be considered for hypergeometric functions. So this somehow this slide illustrates the essential of this essential part of the relation between hypergeometric functions series, hypergeometric series, and the convergence domain associated the convergence domain of this H series and secondary fan. So, for example, we looked at this residue, summation residue that defined by this series. Okay, and then it is you can see that this is somehow it has we can associate cone, this kind of cone, and we look at a cone, dual cone to this. And this exactly correspond to the cone that appeared in the amoeba complement components. So from amoeba, and this amoeba extra components really forms, these cones form a fan. It's a dual fan. And it is related to, it does come from the discriminant of discriminant polytope. So I once again repeat. For example, I can take this one. This is series that is convergent another domain of convergence here. That it is also interpretation as the dual cone to this cone. I remain further. And now this was the local situation, and now my challenge is to get analytic continuation from one domain of convergence to other convergence. So I did analytic continuation. Maybe it's useless. It's analytic continuation. So how do I do the analytic continuation? By means of contour throw that I did it. In the case of Gauss case. So this series contour throws to here, and so on. I get new new series that is convergent to another domain of convergence. So in the case of Gorenstein cone, consider this kind of, I shall start from one convergence domain. And to go past to another convergence domain. To pass to, and then go back. That will give you a monodromy. So the monodromy theorem, the main theorem that is the main tool, it is rather to go from, to start from, this is the analytic continuation result of one series that is convergent one domain. Yeah. And to analytically continue to another domain of convergence, and then go back, then I will get this expression that is somehow an analytic version of Picard-Lefschetz formula. In fact, this is very general toric Picard-Lefschetz formula for associated to affine variety connected related to Gorenstein cone. Okay, this is very
Susumu, you are broken, I guess, huh? Tanabe is well, it seems that Tanabe lost connection. So let's wait for a few minutes. Well, Susumu may not even know that he is disconnected, maybe, huh?
Probably, but he might recognize at some point, hopefully.
I see.
Can you call him?
Sorry. Do you have his Skype or another means of communication?
Yeah.
Well, I mean, I don't have his cell phone, so I could have called him, but I don't have his number. Oh, but maybe, wait a second. Among the participants, Kaan, can you hear me?
Duyuyorum hocam, evet.
Susumu'yu arayabilir misin bir?
Tabii ki hocam. Bir saniye ben arayayım.
Tamam. Adam düştü çünkü şeyden.
Bir saniye. İlhan hocam, ben konuştum, kendisi geliyormuş şimdi.
Bağlanıyor mu? Tamam. Çok iyi. Teşekkürler Kaan.
Bir şey değil hocam.
So we informed Susumu and now he is reconnecting, I hope. He is connected. Okay, now Susumu, you are co-host again.
Unmute yaptım. Geliyor mu?
Ses geliyor.
Ses geliyor.
Görüntü yok.
Görüntü yok.
Hı hı.
Görüntü yok. Var mı?
Videoyu start edin isterseniz.
Screen, share,
tamam.
share.
Tamam. Hı hı.
Join a meeting. Is this? Görüyor musunuz?
Evet, senin ekranını görüyoruz şu an. Siyah bir ekran.
Evet.
Hı.
Şimdi ben açacağım.
Evet.
Görüyor musunuz?
Aa. Siyah ekran. Tamam.
Siyah
Okay.
ekran.
Yeah.
Okay.
So by the way,
Tamam,
you have few minutes. You have to wrap up.
Yes, so I recall the theorem. Okay, ben kapatıyorum. So I recall the theorem of main theorem, that is Picard-Lefschetz formula, corresponding to Picard-Lefschetz formula for Gorenstein cone defined by reflexive polytope. So this is Picard-Lefschetz say analogy. In fact, it is a Picard-Lefschetz formula. In this setting, very general, and it is possible to calculate it. Everything can be calculable. Okay, and I will illustrate the power of this formula in the case of concrete, say, family of affine hypersurface, YS. And this is by Buttereff's construction, known to be Buttereff mirror to generic smooth n+1 Calabi-Yau hypersurface, complete hypersurface in projective variety Pn. So, and the period integral allows this hypergeometric expression, hypergeometric expression. In this case, it's one variable, only one variable. After torus quotient, I got one variable. And so the standard Reissner ring basis construction will give you this kind of course. And I can calculate the monodromy around 0. That's easy. That corresponds to the multiplication by Chern class of the variety. But important thing is, so in connection with, if I turn around the discriminant loci, the essential divisor of essential, the discriminant loci, then I get this third class expression of the monodromy around the discriminant. As you see, that is pseudo reflection. So as in the case of Picard-Lefschetz. Okay, so this is somehow verification of Kontsevich proposal in the case of Calabi-Yau in project variety. So, and this is intersection matrix. In fact, it's possible to calculate intersection matrix from these data. And this will give, so Cn, everything is described in terms of binomial coefficients. So this is Y part, Y. And as for the coherent sheaves, direct category coherent sheaves, it is automorphism given by this Euler characteristic. That is also known to be so it up to shift they coincide. So on this level, we can see, and it is interesting. This group itself is quite interesting to my mind. So it's this is open question. So to which extent is far from arithmetic group, this monodromy group can be embedded into orthogonal or symplectic group, independence of the oddness of n dimension n. This is open question, yes. That's so this kind of thing, yeah. So it's really from group theoretical point of view, this proposes some challenging problem.
Susumu, 1 minute you have.
Okay, so this is Bernoulli polynomials also appear. This is possible. Okay, this was in the one-dimensional case. So and the really two-dimensional case, further the discriminant. I look at, so we can look at this kind of thing. And standard Reissner ring is this, and the hypergeometric function with maybe two, and the discriminant loci will have this form. Fortunately, this has not so difficult. It is parabola and lines. And the upshot is that it is possible to calculate very, very long. It is by means of analytic continuation. Monodromy calculus gives you this result, and Calabi-Yau monodromy Calabi-Yau of Y if as described by means of third class of W. So this also gives evidence to Kontsevich homological mirror type result. Okay, that's that's it. Yeah. Thank you very much.
Thank you very much. So any questions or comments? We have, you see, our next talk is supposed to be at 11:15, so 4 minutes later. But what we can do is maybe we will start 15 minutes, 11:30 maybe. So we will make discussion and give us kind of a break. It's up to you.
Yeah, nice. Yeah, so up to me or up to who?
Up to you, up to
All
the
of
participants. Yeah.
all of participants. Yes.
Yeah.
Yes. Yes, yes.
Yes, please, Ismail.
Thank you for your very beautiful talk. So actually, I'm not sure that my question gonna be kind of relevant question. Maybe that would be a super silly one. But is there sort of connection to the S-duality from this sort of works or not? Or is
S-duality.
by a speculation or something? Yeah.
Yes, yes, yes, yes. But it is, so, you know, so mirror symmetry has different versions, quite different versions. And homological mirror symmetry is supposed to be the strongest one. Homological mirror, this refers this categorical equivalence.
So I'm actually asking that because I'm like sticking the tunnel to the Langlands program, to the geometric Langlands program. Content of my
that can be that side I don't know well, but anyway, so especially so it is. There are two types of the strongest mirror symmetry proposal. One is this homological mirror symmetry. Other was ESZ of Zaslow. This Lagrangian fibration proposal, yes. And maybe S2 can be formulated in terms of the Lagrange fibration side. But everything is quite speculative, most of the speculative level. But it is believed that homological, so in certain cases it is proved that homological mirror symmetry really implies other, so Hodge number or Gromov-Witten invariants, this kind of thing. Everything follows from this. Yeah, it has been proved in certain cases. But not for every case. So it is on the on the way of speculation. Yes, quite. That's the state here. And I work very small part, somehow this part, and somehow it can be that if it contribute to go from this side to this to auto equivalence, plus some information will give this categorical equivalence. that can, yeah, I don't know. Yeah.
Susumu, can I ask a question?
Yes.
So this homological mirror symmetry conjecture of Kontsevich,
yes,
stated only for Calabi-Yau varieties?
Yes, it is. It is. There is a version for Fano variety. In fact, it is. I talked to two kinds of Stanley-Reisner ring. One is affine and one is. This is how to. Roughly speaking, this affine power case is Landau-Ginzburg potential case. Yeah. So there is another formulation. In fact, there are some generalization to the case of non-Calabi-Yau case also, Fano variety case also, yes. And of course, I work on that, but it requires some quantum cohomology and so on. That it is related. So it is a huge range, and there are many evidences and how to glue all of them to put into one coherent vision. No? That's a challenging story, and I don't know. In Iran, there are people who are working on mirror symmetry. I never read articles by Iranian mathematicians.
Maybe physicist. There is Kumrun Wafa at Harvard, string theorist. I am sure he is interested in this, right?
Who?
Wafa.
Harvard. Eh?
Wafa.
Oh, Wafa. Of course. No. Wafa. Wafa, of course. Hori Wafa is one of the inspiration of somehow it is. Yes, I work on such kind of situations also. But, yes. No, but Hori Wafa were classics. Yes.
Sheikh Jabbari also has some works in that direction.
Who?
Sheikh Jabbari, so belongs to the physics department of IPM. So he was.
Oh, really?
I mean, I have seen that in some of the articles of Edward Frankel. So he mentioned that.
Ed Frankel.
And therefore, there would be. I mean, I assume. Not sure.
In any case, I want to repeat again that I really want to visit Tehran. So next time I can give a more arithmetic related talk on Dwork homology or Dwork.
So I keep my questions for your next talk. So
So I hope that we meet next year, so certain moment in Tehran, and the second this meeting will take place in Tehran. Yes, and I can visit. This is a very wonderful occasion to acknowledge.
Well, let's hope that next year there will be no COVID.
Yeah.
Okay, so let's thank our speaker once more.
Yeah, thank you very much. Shukran.